Well, so far the examples, you know, again, this partial fraction decomposition is just another tool you put in your toolbox. Whenever we're integrating a proper fraction, that is a proper rational expression, then this is a tool that we can try. And maybe it's not always the easiest, maybe it's not always the best, but it's certainly something that we can try if we're needing to integrate. And so far, the examples we've looked at have been fairly routine in terms of the integrals that we're left to deal with. And so what I want to do is give you some examples where it goes along in a routine way, but we're also going to run into some issues occasionally that we have to use additional techniques of integration as we proceed. So in this next example, we actually have a denominator that has distinct quadratic factor, irreducible quadratic. Remember that terminology. And we're talking about the denominator. So we're asked to evaluate the integral of x plus 3 divided by x to the 4th plus 9x squared. With respect to x. And since I can't see a substitution that would quickly work for me, then, I mean, I'm considering several possibilities, but I can't let u be x to the 4th plus 9x squared, because du, I have nothing that looks like that at all. You know, du would be 4x cubed plus 18x, and there's nothing in the numerator that would make me think that that's going to work. So I'm going to try this idea of partial fraction decomposition. So I'm going to take, before I get very far into this, I'm going to take my fraction that I'm integrating, and I'm going to factor it completely. And when I do, I'm going to factor the denominator. When I factor out an x squared, I'll have x squared times x squared plus 9, and we recognize that we can't factor x squared plus 9 any further. So we know that this decomposition is going to have 3 fractions. It's going to decompose into 3 fractions. And you may say, well, why? Oh, remember, x squared. X is the factor, and it's squared, so we're going to have a denominator of x to the 1st and a denominator of x squared. Okay, be careful of that. And then we're going to have a denominator of x squared plus 9. Okay, the 2 factors, but because of the repeated factor x, we had to be more careful. Now, this first fraction is going to have a linear numerator. The second fraction is also going to have a linear numerator. And the confusion can be, oh, I see an x squared. But the factor is x. It's repeated. So when we're looking at the factor as x, then that's first degree, and so the numerator is 0 degree or a constant. Now, the third fraction, we can't factor x squared plus 9 anymore, so the factor is x squared plus 9, which is quadratic, and so this is going to have to be a linear numerator, so it's going to be of the form cx plus d. Now, as I multiply out the denominator x squared times x squared plus 9, I'll have an x plus 3, and I'll have an x squared plus 9 times a, and an x times an x squared plus 9 times a, okay? And then I'll have, in the second, the x squareds will cancel, so I'll just have an x squared plus 9 times a b. And then lastly, the x squared plus 9 will cancel, but the x squared won't, so I'll have x squared times cx plus d. And I continue here, and I'll get, what, x cubed plus 9x times a. And I'll have, well, we'll just say x squared plus 9 times b. and then plus, well, this will be cx cubed plus dx squared. And I guess I'll have an ax cubed plus a 9ax plus a bx squared plus a 9b plus a cx cubed plus a dx squared. Now, I'm looking at my x cubed terms. I have two of them, a plus c, because those are the two x cubed terms. A plus c is the coefficient of x cubed. And since there's no x cubed term on the left side, a plus c must be 0. Then I'm looking at my x squared terms. So when I combine those coefficients, b plus d, well, b plus d must also be equal to 0 because that's the coefficient of x squared, and on the left side I have no x squared terms. Then I'm looking at my x to the first power term, and it looks like there's only one, isn't there? That's only one. So 9a, coefficient of x, must be equal to 1. And now I'm looking at my constant term, 9b, and so 9b must be equal to 3. And all of this together tells us, as we solve for, well, actually, I guess I don't know. Certainly right here, I get a is 1/9. And down here for the b, I get b is 1/3. And so since I have a is 1/9, I have 1/9 plus c is equal to 0. So c is negative 1/9, isn't it? And since I know b is 1/3, right here I've got 1/3 plus d is equal to 0. So that tells me that d is negative 1/3. Okay. So my integrand, x plus 3 over x squared times x squared plus 9, decomposes in a fashion where I have a 1/9 over x plus b 1/3 over x squared plus c times x, that's negative 1/9 times x, plus d, which is, whoops, minus 1/3, and all that is over x squared plus 9. Okay, we still have our work cut out for us, because what we're doing now is we're integrating, of course, x plus 3 over x to the 4th plus 9x squared with respect to x. But that's what this is equal to right here, not the integral, that's what we're integrating. So we're going to write this into multiple integrals. We're going to have the integral, let's say, we'll go ahead and factor out the 1/9. So we'll have the integral, 1/9 times the integral of 1 over x dx, plus the integral of 1/3 over x squared. We'll factor out the 1/3. So we have the integral of 1 over x squared dx. And then finally, we have the integral of, and I don't see a whole lot that we can easily do with what we see there. And so I guess my approach here is we'll just write down with this, what you say, we're kind of writing what we can and hoping we get an idea of what to do in a moment. So this is the integral that we're dealing with. Okay. Now, let's deal with, of course, these first two pieces. Okay, in this first integral, of course, the integral of 1 over x with respect to x is nothing more than the natural log of the absolute value of x. So we have plus 1/9 times the absolute value, the natural log of absolute value of x. In the second case, the integral of 1 over x squared is negative 1 over x. So we end up with plus a 1/3 times a negative 1 over x right here. But we still have a big mess over here. Okay. Obviously, we can clean this up. Okay, we can clean this up. This is 1/9 times the natural log absolute value of x. We'll say minus 1 over 3x. But plus still, what are we going to do with that? Well, let's move to the next page and let's deal with that integral alone. Okay, and then we'll come back and finish this problem. Okay, so we need to deal with this last integral. Whoops, except it's, I miswrote something, didn't I? I see I did back on the previous page. Let me fix that. This is really, I'll fix that later. I'm sorry. I know you can hear the rustling going on here. This is a minus 1/9. Okay, and I think on the previous page I put a minus 1/3 x. So minus 1/9 x minus 1/3. Now, this looks, I don't know an easy way to explain except to have you be thinking of things in the future. And here's what I want to remind you of. If we let u be x squared plus 9, then if we did the substitution, then du would be a 2x dx, wouldn't it? And the x dx is what I'm concerned about, not the 2. We can deal with the factor of 2. But my numerator is much more complicated than just an x dx, isn't it? But what I would remind you here is if we looked at just this part of what we're dealing with over there, if we just looked at that part, then we could factor out that negative 1/9, and we'd have the integral of x over x squared plus 9, wouldn't we? And this looks similar to what we would need if we were making that substitution. We could deal with that. But what are we going to do with the rest of that integral? Because then we'd also have an integral of negative 1/3 over x squared plus 9. So we'd also have that. I'm not trying to make this neat. I'm telling you what's going on in my mind, or why I'm trying to explain how to explain what we're getting ready to do. Now, in that case, I could factor out a negative 1/3, and I have the integral of 1 over x squared plus 9 with respect to x. And then I recognize that this is an inverse tangent form. So if I break this apart, and we've seen this before, if I break this one integral apart, so here's what I'm going to do. I'm going to break this integral apart by thinking of it as the integral of negative 1/9 x divided by x squared plus 9 with respect to x, plus the integral of negative 1/3 over x squared plus 9 with respect to x. Because if I added those two fractions together, I'd get my original. And then I'm going to factor out that negative 1/9 factor in the numerator of this first integral, so it looks like this. And I'm going to factor that negative 1/3 out in the numerator of the second integral, and it looks like this. And now the hope is that we can see that we can deal with these. See, what we would do here is we would let u be x squared plus 9, and du would be 2x dx. So in this first integral, what I'm going to do is I'm going to create my u by saying 2 times x, okay, and x squared plus 9 down here. But if I put a factor of 2 in the numerator, there I've got to offset it by a factor of 1/2 on the outside, okay, dx. Now remember, this is u, and this is du. We're going to come back to that in a second. Minus 1/3, and here I recognize that this is of the form 1 over a different u, of course, u squared plus a squared, okay? And because u and x are the same here, du and dx are the same. So that's a du. And this is the inverse tangent form, isn't it? The result here would be the inverse tangent of, what is it? U over A. Actually, my bad. It's 1 over A times the inverse tangent of U over A. And so we have a way of completing that. Well, okay, let's go back from the beginning here now. So in this integral, let's not forget what we were doing because I've been all over the place here. In front we have a negative 1 over 18. And we have a denominator of u, and 2x dx is du. And so in this case, that's the natural, that integral is the natural log of the absolute value of u, but u is x squared plus 9. And over here we have the factor of minus 1/3. And what we're integrating, remember, the u is x and the a is 3. So we have times a 1 over a. Okay, so we have another 1/3 times the inverse tangent of u over a. And u, of course, is x, and a is 3. And then we'll have our constant of integration because we've got part of this integral over on the other page, don't we? And so there's a couple things we can do yet here. Let's make sure that we understand. A lot of times you'll notice that absolute values disappear, and that's because x squared plus 9 is always going to be positive, and so absolute value is not really necessary there, is it? And of course here we have a negative 1/9 times the inverse tangent of x over 3, and like I said, we'll deal with the plus constant as we finish the problem. So remember, this is just the integral that we had here, which is our third integral. So our answer, remember what we were doing. We were integrating x plus 3 divided by x to the 4th plus 9x squared. And we broke it into 3 integrals by doing a partial fraction decomposition. And as we did that, the first 2 integrals, we got 1/9 times the natural log of the absolute value of x. And the second one, we got minus 1 over 3 times x. And this third one that we were just working on actually is, I suppose we could write this as a minus now, because we have a minus 1 over 18 times the natural log of x squared plus 9. And then another minus 1/9 times the inverse tangent of x over 3. And finally, plus our constant of integration. So that was quite involved, wasn't it? Although we were doing partial fraction decomposition, we had to remember several other things involved. And that's not going to be unusual for us. Well, the next example also has something. I've got 2 more examples I want to do for you, and they have important things that we need to be careful of and recognize that it's not always straightforward. Okay, here we are to integrate again, and notice that the degree of the denominator, I have to be a little careful here, but this is in factored form, and in factored form, the denominator is x squared plus 4 squared. So if this was not in factored form, the degree of the denominator would be 4, wouldn't it? And the degree of the numerator is 2. And so this is, in fact, a proper fraction. Okay. Now, that means partial fraction decomposition is an option. Whether it will help, I don't know, but I don't see how to do it without trying that. And so we're kind of starting down a path. Now, notice here, the denominator is also already factored as much as we can. X squared plus 4 is an irreducible quadratic. So this is a repeated irreducible quadratic denominator. I'll just say repeated quadratic factor in the denominator. Well, I trust that you could decompose this Okay, so well, I guess let's do it. X squared over x squared plus 4, the quantity squared. Now when we decompose it, we're going to have two fractions. One's going to have the denominator x squared plus 4 to the first, and the other one's going to be x squared plus 4 to the second. Now, because this is a quadratic denominator, the numerator is linear. Whoops, 8x plus b. And we still have a quadratic factor for our denominator, although it's repeated, for the second fraction. So its numerator is also linear. So I'll say cx plus d. Okay. Now we multiply out that denominator, x squared plus 4, the quantity squared. And so we'll have one of the factors of x squared plus 4 squared cancel, and we'll still have times an ax plus b. And over here, we'll have both of the x squared plus 4 factors cancel, and so we'll just be left with cx plus d. Now, as we continue, and we multiply out this first quantity, what will we get? Ax cubed plus bx squared plus 4ax plus 4b plus cx plus d. Now, ax cubed is our only cubed term, and there's no cubed terms on the left, so we know a is 0. Oh, this is bx squared, isn't it? Instead of bx, my bad. X squared times b. Okay. We have only one x squared term here on the right, and we have one x squared term on the left. Coefficient on the left is 1, so b must be equal to 1. Likewise, what do we have in terms of x? It's to the first power. We have a 4ax plus a cx, so 4a plus c is the coefficient of x, and on the left side, the coefficient of x is 0. And then we have the constant 4b and the constant d, 4b plus d. On the left side, the constant 0, so 4b plus d is 0. So here's where we are with this then. All of this stuff together, we know, of course, a is 0, and b is 1. And when we put our a into the equation 4a plus c, we get c is 0. And when we put a b of value of 1, we get d is negative 4. Okay, so now we know all of our values. So when we go to integrate this, so we've done, or we've got the composition, the decomposition set up. So when we go to integrate x squared over the quantity x squared plus 4 being squared, we're just doing nothing more than integrating. A is 0, b is 1, so we're integrating 1 over x squared plus 4, our first fraction, plus the second fraction, cx plus d, over x squared plus 4, the quantity squared. So in that case, our d is negative 4, isn't it? So we have a negative 4 over, and our c is 0, pardon me. So we have 0 times x plus d, and d is negative 4, over x squared plus 4, the quantity squared. So that's what we've changed our fraction into. So we have two integrals to deal with. Okay, well, to deal with this one is simply an inverse tangent deal. Okay, inverse tangent. And in fact, in this case, the a is 2, so we'll have 1/2 the inverse tangent of x over 2. Now over here we can put that minus sign down and make a subtraction in between these, but here we're going to have to use trig substitution. Yeah, we can't forget that old stuff. Still have to use it. And what we would do is we would replace x with 4 tangent of theta. Okay, well let's begin the process, and we might make this a little more abbreviated. In this first, well, let's just write it out. We have the integral of 1 over x squared plus 4 with respect to x, minus the integral of 4, let's factor out the 4, of 1 over x squared plus 4 squared with respect to x. And this first integral is inverse tangent directly, so we have 1/2 times the inverse tangent of x over 2. That's u over a. 1 over a, times inverse tangent of u over a, x over 2, okay? Now remember, u was x and a was 2. Now, in the trig function business over here, we're going to have to come back and we're going to have to deal with this. So here's the substitution we're making. And we're going to come back, we're going to deal with this, and then we're going to come back and finish the problem like we have been. So when I'm looking at the integral of 1 over x squared plus 4, the quantity squared, with respect to x, I'm going to try, because I'm recognizing x squared plus 4 here. I can't do any other kind of substitution that's clear to me. So if I replace x with 4 tangent of theta, then this is going to be the integral of 1 over, not 4 tangent of theta, but 2 tangent of theta. Okay? My bad, way up here, that should have been a 2 tangent of theta. So then I end up with, when I square x, I get 4 tangent squared theta plus the 4 that's already there, and that's squared. I need to replace dx with a d theta. And in this case, dx would be, 2 secant squared theta, d theta. So I have here a 2 secant squared theta d theta. Okay, well, how's this going to work out? Well, in this denominator, I can factor out a 4, and that's going to be squared. So here's what, well, let's do it this way. I have a 4 times tangent squared theta plus a 1, and that whole denominator is squared. And of course, this 2 secant squared theta d theta that I haven't dealt with fully yet. But inside here, I have nothing more than secant squared theta. So this integral is going to be 1 over 16 secant to the 4th theta times 2 secant squared theta d theta, and I'm going to get some action in simplifying, aren't I? Okay, on the next page. Okay, that's where we are, and we can see we have 2 over 16, which is a 1/8. Let's go ahead and factor that out. And secant squared over secant to the 4th is going to be 1 over secant squared theta d theta. Now 1 over secant squared theta is nothing more than cosine squared theta. Okay, well, let's see what we've got here. Oh, this may be some bit of work for us. This actually, maybe I should have just told you you're going to do this with trig substitution and clean my hands of it. Well, we're going to have to use we're going to have to deal with integrating cosine squared theta by using a power reduction formula, aren't we? So we're going to write cosine squared theta as 1/2 times 1 plus cosine of 2 theta. Okay, so we have a 1/8. Oh, well, I guess it's a 1/16 if we factor that 1/2 out, isn't it? 1/16 times the integral of 1 plus cosine of 2 theta. I think we can deal with that. So 1/16, the integral of 1 with respect to theta is theta. The integral of cosine of 2 theta is 1/2 the sine of 2 theta. So we have 1/16 times theta plus 1/32 times the sine of 2 theta. Those are constant of integration, but this is just part of the problem that we were starting with, if you kind of recall. And I hope that you're using the pause and the rewind and making sure you understand, because occasionally I get to going pretty fast here, and it still takes a long time. Okay, so what we're going to have to do at this point is change these things back into x's. Okay, so we're thinking about our representative right triangle where this is theta. And remember, we started out with saying that x is 2 tangent of theta. That's what we started out with, 2 tangent of theta. And so tangent of theta itself, looks like I'm running out of ink, is x divided by 2. And so, and tangent is opposite over adjacent. So we could name the sides in this fashion, and we'll use the Pythagorean theorem to calculate this hypotenuse. We'd get it as the square root of x squared plus 4. So we would find out that that's equal to. Okay. Well, there's several things. One, if we want to know theta, see, we need to know theta, don't we? Well, we look right here and we say, oh, well, that tells us that the inverse tangent of x over 2 is equal to theta, or theta is the inverse tangent of x over 2. Okay, so we've got that handled, I guess. Now, what else do we have? Well, we need to figure out what the sine of 2 theta is. See, that's the next thing we're worried about. But we don't have anything up there that tells us about the sine of 2 theta. We don't see an angle of 2 theta. So here's what we're going to do next. To figure out what the sine of 2 theta is, we remember the identity, the double angle identity, that's 2 times the sine of theta times the cosine of theta. And now we can use that triangle to figure out each of those. So sine of theta is opposite over hypotenuse. Cosine of theta is adjacent over hypotenuse. So now we have the sine of 2 theta. So in place of theta, we put inverse tangent of x over 2. And in place of sine of 2 theta, we'll put in, let's look over there, because this is really a 4x in the numerator over, when we multiply those denominators together, we just get x squared plus 4, don't we? So it's times a 4x over an x squared plus 4. And I suppose we can clean that up a little bit more. We have a 1/16 times the inverse tangent of x over 2, plus we have a 4 over 32, which is 1/8, isn't it? So this is an x over 8 times x squared plus 4. Now, let's not forget what we were doing. Okay, we were integrating x squared over x squared plus 4, the quantity squared with respect to x. And we used partial fraction decomposition, and we got it to a point where we had 1/2 times the inverse tangent of x over 2 minus 4 times the integral of 1 over x squared plus 4, the quantity squared. And this is what we were just working on. That's our replacement right there, isn't it? So we end up with a 1/2 times the inverse tangent of x over 2 minus 4 times the result we just got here, which is 1/16 times the inverse tangent of x over 2 plus x over 8 times x squared plus 4, and plus a constant integration. Now, I am kind of running out of space here, so I'm going to do some arithmetic in my head. When we distribute this negative 1/4, we're going to have a negative 4 over 16, or 1/4, tangent of x over 2. We have 1/2 of them, and we're minusing 1/4 of them. So we'll be left with 1/4 inverse tangent of x over 2. We're combining those two inverse tangents. And then we have a negative 4 times that. When we distribute the negative 4, multiply over here, well, the 4 over the 8 is going to cancel this. We're going to have a minus x over 2 times x squared plus 4, plus the constant of integration. So, well, don't worry. We won't have more than 10 problems like this on our homework. That wasn't really funny, was it? We won't have many problems that take this long, but we need to be prepared to use additional techniques other than what we started with, which was partial fraction decomposition. Okay, I have one last example. And I'll do it on the next page. In this last problem, we're to evaluate the integral x cubed minus 2x over x squared plus 3x plus 2. We get all excited because we're in the mode of using partial fraction decomposition, and we'll run into trouble unless we notice that this is an improper fraction. It's a problem. Okay. Well, the whole idea about an improper fraction, just like when we're dealing with numbers, if we had 17 over 5, that's an improper fraction, meaning that 5 will divide into 17. It won't divide evenly, but it will divide in how many times? 3, plus a remainder of 2? So we'd say 3 plus 2/5 more. Okay, that's 17 over 5. And that kind of gives us the hint of what we really want to do. When we have an improper fraction, we want to perform a long division. So we're going to divide x squared plus 3x plus 2, and since it's of lesser degree than the numerator, it will divide into it. I'm going to write the numerator x cubed minus 2x. I'm going to write it as an x cubed plus a 0x squared minus a 2x, and then I guess plus a 0, so I have powers all the way down to a constant. And I say, okay, well, how many times will this x squared go into x cubed, and it will go x times? And so I put my x right here in the x column, and I multiply x with x squared plus 3x plus 2. So I get x cubed plus 3x squared plus 2x. And then I subtract. And I'm not trying to teach you how to do long division. I hope that you know that already, but if not, go find some source to refresh your memory. X cubed minus x cubed is 0. 0x squared minus 3x squared is negative 3x squared, Negative 2x, subtract a positive 2x is minus 4x. And now we begin again and say, well, how many times will x squared go into negative 3x squared? And of course it goes a negative 3 times. So we multiply negative 3 with that whole divisor, and we get negative 3x squared. we get minus 9x. And we get, what, a minus 6. And then we subtract. Negative 3x squared, subtract a negative 3x squared is 0. Negative 4x, subtract a negative 9x is a positive 5x. And 0 subtract negative 6 is a plus 6. Now our remainder is lesser degree than our divisor, so we cannot divide anymore. So what we have found out is that if we this fraction x cubed minus 2x over x squared plus 3x plus 2, when we do a division, we get x minus 3 plus the remainder 5x plus 6 divided by x squared plus 3x plus 2. Okay, well, that is the secret of this. So when we're trying to integrate x cubed minus 2x over x squared plus 3x plus 2 with respect to x, it's the same as integrating the result of our division, which is x minus 3 plus this fraction 5x plus 6 over x cubed plus 3x plus 2. Now, these first two pieces of the integral are easy, aren't they? The integral of x is 1 over x squared. I'm sorry, I don't know where my head is. I guess I'm trying to finish this. Is 1/2 times x squared minus the integral of 3, which is 3x. Now, to integrate this, we would use partial fractions. So I'm not going to stop and do that. I'm just telling you now we would look at that fraction, which is a proper fraction, and we can except this is an x squared too. I'm making all kinds of problems at errors here. That's an x squared plus 3x, isn't it? Anyway, we could use partial fraction decomposition on this. And if we did, we'd find out that this fraction would actually end up being 1 over x plus 1 plus 4 over x plus 2. You could verify that. And so the bottom line is, and again, I'm not verifying this for you, I'm just telling you, when we continue our integration, when we integrate 1 over x plus 1, we'll get the natural log of the absolute value of x plus 1. And when we integrate 4 over x plus 2, I'd factor out the 4, and then we'd have the integral of 1 over x plus 2, which would be the natural log of absolute value of x plus 2, plus our constant of integration. So the deal is, what happens if we have an improper fraction? Well, we first have to divide and get a proper fraction, and of course integrate the other pieces that come with it. Well, I know this has been a long discussion. I hope that it gives you plenty of examples so you're prepared for anything your homework or a test might throw at you. Until next time.